My dear students, last time we have seen what are opposing reactions and the chemical kinetics of opposing reactions. With this, let us see today what are consecutive reactions and the chemical kinetics of consecutive reactions. Let us see at first what are consecutive reactions. What are consecutive reactions? A reaction which takes place in two or more than two stages or steps, one after another, without any interruption, is known as a consecutive reaction or sequential reaction or successive reaction. We know what is the meaning of consecutive or successive or sequential. All these are adjectives. Consecutive, anything taking one after another is known as a consecutive thing, or consecutive days, consecutive weeks, consecutive months, something like that. One after another. Consecutive numbers, consecutive numbers 1, 2, 3, 4, 5. So 2 comes after 1, 3 comes after 2. So these are what the few examples of consecutive numbers. So in a very similar way, a chemical reaction which occurs in two or more than two consecutive steps, successive steps, sequence steps taking place in a sequence, is known as a consecutive reaction. So let us have one simple hypothetical example of a consecutive reaction. Let us suppose a chemical reaction is a consecutive reaction, and the overall reaction in that case is A giving what? D. A is reactant and the final product is D. So in this case, how this consecutive reaction takes place, or how this transformation, how this chemical conversion of A into D occurs. The conversion of A into D occurs indirectly. How? Let us suppose in this case A is converted into B plus C, and later on this B is converted into what? D. So here this conversion, this type of conversion, A giving B plus C and B is giving what? D. Isn't it? So such type of chemical reactions taking place in the successive steps, two or more than two successive steps, consecutive steps, are known as consecutive reactions. So when we look at this hypothetical example of a consecutive reaction, we will see that reactant A is at first converted into B and C. So B and C are the new products in this particular case, and these two new products later on are converted into the final product. So in this case, product B is converted into D. So the overall reaction in this case is A is giving what? C plus D. So here the transformation, this chemical transformation, this chemical conversion, the conversion of reactant A into the final products C and D does not take place directly, but it takes place via some intermediate step, some intermediate product B, and therefore such type of reactions which are taking place in two or more than two successive consecutive steps are known as consecutive reactions. So let us have few examples of consecutive reactions. Now, the best examples of consecutive reactions are: number one, thermal decomposition of acetone. Thermal decomposition of acetone. What happens when acetone decomposes? Of course, when we supply appropriate amount of heat to a given amount of acetone, acetone decomposes and gives what? Ethene, carbon monoxide and methane. So the overall thermal decomposition of acetone is converted into ethene, carbon monoxide and methane. But this conversion, whatever the conversion of acetone into the final products, ethene, carbon monoxide and methane, does not take place in a single step, but it takes place in two steps. This reaction, the thermal decomposition of acetone, occurs in two stages or two steps. Let us see how the thermal decomposition of acetone occurs in two steps. In first step, what happens? Acetone, CH3, C double bond O, CH3 is converted into H, C double bond, C double bond O, H plus CH4. Okay. And this new product generated in step 1 is later on gives what? The 1 by 2 C2O4 plus CO. So this is what the second step. So I can write it here like this. This is what the step 1, step 2, step 2, H, C double bond, C, O, H gives what? 1 by 2 C2O4 plus CO2. So this reaction, the thermal decomposition of acetone, occurs in two steps. This is what the first step, and this is what the second step. So this is a very good example of thermal the consecutive reaction or the sequential reaction. Here the conversion of acetone into methane, carbon monoxide and ethene gas occurs in two steps. In first step, acetone is converted into these two products. Out of these two products, this product is converted in second step into ethane and carbon monoxide. So in this way we have seen what is a consecutive reaction. I am sure you must have understood what is consecutive reaction and how the consecutive reaction occurs. So with this, let us see one more example of consecutive reaction. Hydrolysis of diethyl succinate. Hydrolysis of, second example is hydrolysis of diethyl succinate. We know that when any ester, diethyl succinate is a ester of what? Succinic acid. So we know in general when any ester undergoes hydrolysis, it gives the corresponding what? Alcohol and the acid. So in this case, when diethyl succinate undergoes hydrolysis, it must give what? Succinic acid and the ethanol. So the reactant in this particular case is diethyl succinate and what? The water. So when we put diethyl succinate in water, it undergoes hydrolysis and gives what? The final products, succinic acid and ethanol. This conversion, this transformation of what? Diethyl succinate into succinic acid and ethanol does not take place in a single step, but it takes place in two steps. Let us see how diethyl succinate is hydrolyzed and gives the final products, succinic acid and ethanol, via some intermediate step. So in first step, what happens? Diethyl succinate, CH2, COO, C2H5, CH2, COO, C2H5. Diethyl succinate. Two ethyl groups are there. Diethyl succinate plus HOH, that is water. H2O. No, H2O. I can write it like this. H2O. HOH. Okay, so when diethyl succinate is added in water, it undergoes hydrolysis and in first step monoethyl succinate is obtained. CH2, COOH, CH2, COO, C2H5 plus ethanol plus C2H5OH. Isn't it? So when we look at this, we will see that in first step, diethyl succinate undergoes hydrolysis. Partial hydrolysis of diethyl succinate takes place in single step, and what we get? We get this product, and this product, a new product generated in this reaction in first step, is later on converted into the final products. CH2, COOH, CH2, COO, C2H5 plus HOH gives CH2COOH, CH2COOH plus C2H5OH. Okay, so in this way, this is step 1, this is step 2. So in this way, the hydrolysis of diethyl succinate occurs in two steps, and therefore this is an example of consecutive reaction, and these two steps, step 1 and step 2, takes place one after the other without any interruption, and therefore this reaction is known as a consecutive reaction or sequential reaction or sometimes successive reaction. So with this, I am sure you have understood what are consecutive reactions. So with this, let us switch over to the kinetics of consecutive reaction. The kinetics of consecutive reaction is very important because, as we have seen, consecutive reactions involves various steps, and therefore we must know which one is the slowest step, and once we know that, using that slowest step, we can find out what the rate constant of the reaction. So let us see the chemical kinetics of consecutive reaction with the help of a simple hypothetical example. A is giving B and B is giving C. And let us suppose the rate of this reaction, the conversion of A into B is K1, and the rate of this reaction, what the conversion of B into C is K2, where K1 is not equal to K2. Okay, let us have this hypothetical example of a consecutive reaction in which A gives what the C. A is reactant, C is product. But here, this transformation, this conversion, the conversion of reactant A into C does not take place directly. It occurs in two steps, or the conversion of A into C takes place, no doubt, but via what? New product B. So let us see how can we discuss, how can we explain kinetics of this consecutive reaction. Now, this is what the simplest case of consecutive reaction in which both these stages are of first order. Look at this. A is converted into B, B is converted into C. So this is what the in this consecutive reaction, both the reactions, the conversion of A into B and the conversion of B into C is what? The first order reaction. A conversion of A into B is first order reaction. Conversion of B into C is also a first order reaction. Rate of this reaction, the conversion of A into B, depends upon the concentration of only one reacting species. Therefore, this is obviously a first order reaction. Again, here the conversion of B into C is again the rate of this conversion, the rate of this reaction depends upon what? The concentration of B. In other words, this is also a first order reaction. Let us suppose small a is initial concentration of A. Let small a is initial concentration of reactant A, and let X, Y, Z denotes concentrations of A, B and C respectively at time t. Okay. Hence, we can write small a is equal to x plus y plus z. And let us suppose this is equation number 2. Okay. This is equation number 1. Okay. And this is equation number 2, where small a is equal to x plus y plus z. Now, let us see at first the rate of disappearance of A. The rate of disappearance of A is minus dA, or rather here dx upon dt is equal to k1 into x. This is what the equation number 3. The rate of disappearance of reactant A is minus dx upon dt is equal to k1 into x. When we look at this, we will see that this expression also represents what? The rate of formation of B from A. Okay. So, this equation, the equation number 3, we can rearrange equation number 3 and write it like this: d minus dx upon x is equal to k1 into dt. Equation number 4. Integrating equation number 4. Now this is what the separation of variables. What we did, when we look at this, we will see that here there are two variables x and t. What we did, we have separated variables. We have taken the x terms on one side and the t terms on another, t term on another side. So this is known as the separation of variables. So on separating the variables, what we got? We got minus dx upon x is equal to k1 into dt, and let us suppose this is equation number 4. Now this is a differential equation and we can very easily integrate it. So integrating equation number 4, we get minus natural logarithm of x is equal to k1 t plus I c, or simply I, and this is equation number 5. Okay, where I or sometimes IC is integration constant, or known as constant of integration. Now the value of integration constant IC can be very easily obtained. How? Putting t is equal to, or when t is equal to 0, x is equal to a, and therefore the equation number 5 becomes minus natural logarithm of a into minus natural logarithm of a is equal to IC. Okay, so when we look at this, we'll see that when we substitute t is equal to 0, so 0 into k1, it becomes 0, and natural logarithm of x, so x is equal to what? A, so obviously we get minus natural logarithm of a is equal to IC. And let's suppose this is equation number 6. Okay, so in other words, integration constant IC is equal to minus natural logarithm of a. Let us substitute IC is equal to minus natural logarithm of a in equation number 5. So what we gain when we substitute what IC is equal to minus natural logarithm of a in equation number 5, we get minus natural logarithm of x minus natural logarithm of x is equal to k1 t minus natural logarithm of a. Okay, and we can rearrange this equation. Rearranging this equation, what we get? Natural logarithm of x minus natural logarithm of a is equal to minus k1 into t. Okay. Now this equation, we can convert this equation, or we can write this equation in a little bit different way. How? Natural logarithm of x minus natural logarithm of a, what does it mean? It means according to what the laws of logarithm, this equation is natural logarithm of x upon a is equal to minus k1 into t. Okay, and taking antilog of this, what we get? We get x is equal to a into e to the power minus k1 into t. So taking anti-logarithm, what we get? X is equal to a into e to the power minus k1 into t. And let us suppose this is equation number 7. Okay. So in this way we have got an expression for what? X. Isn't it? And what is X? The concentration of A after time t. So with this, let us uh, see the rate of formation of C. The rate of formation of C is given by dz upon dt. dz upon dt is equal to k2 into y, and this is suppose equation number 8, where k2 is the rate constant for the formation of C from B. Isn't it? You know, in this reaction K2, this is K1. So the rate constant of formation of C from B is K2. So dz upon dt is equal to K2 into Y. This is what the rate law of formation of what? C from B. Okay. So as the rate of formation of B is given by K1 into X, and the rate of decomposition of B into C is given by K2 into Y, the rate at which B accumulates, that is dy upon dt. Okay, we know the rate of formation of B is given by expression. Rate of formation of B is given by expression what? Dx upon dt is equal to K1 into X, and the rate of formation of C is given by R is equal to K into Y. So here the rate at which B accumulates in the system is written as the rate at which B accumulates in the system is given by dy upon dt is equal to minus dx upon dt minus plus dz upon dt is equal to minus dx upon dt is equal to minus dx upon dt minus dz upon dt. Equation number 9. Okay. So dy upon dt, here dy upon dt, and what is dy upon dt? dy upon dt gives us what? The rate at which B accumulates in the reaction mixture. So the rate of formation of B, in other words, is equal to minus dx upon dt minus dz upon dt. So let us suppose this is equation number what? 9. Now substituting equation number 3 and equation number 8 in equation number 9. Substituting equation number 3 and equation number 8 in equation number 9, we get minus or rather dy upon dt is equal to k1x minus k2y. Okay. Now substituting the value of x from equation number 7 in above equation, we get, let us substitute what? the value of x from equation number 7 in above equation, we get dy upon dt is equal to k1a into e to the power minus k1 into t minus k2y. Equation number 10. Okay. Now again, when we look at this equation number 10, we will see that this equation number 10 is a linear differential equation of the first order, and the solution of this equation number 10 is a linear differential equation of first order. And when we solve this first order differential equation, first order linear differential equation, we get certain solution, and the solution of this is what? Y is equal to, when we solve this linear differential equation, we get y is equal to a into e to the power minus k1 into t in bracket k1 into e to the power k2 minus k1 into t upon k2 minus k1 minus k1 upon k2 minus k1 bracket close. Let us suppose this is equation number 11. Okay, so the solution of this first order linear differential equation is y is equal to a into e to the power minus k1 into t into in bracket k1 into e to the power k2 minus k1 into t upon k2 minus k1 minus k1 upon k2 minus k1. Equation number 11. Or equation number 11 can be further reduced and written in different way. Y is equal to a into y is equal to k1a upon k2 minus k1 in bracket into e to the power minus k1 into t minus e to the power minus k2 into t bracket close. Okay, so y is equal to this. Okay, so this is what the equation number 12. So in this way we have got an expression for y. Okay, so we know now what an expression for x, we know the expression for y is this. The expression for x is equation number 7. Equation number 7 is an expression for what? X. Equation number 12 is expression for y. However, we know that A is equal to x plus y plus z, isn't it? And therefore, obviously, z will be equal to A minus x minus y. This is equation number 30. At the very beginning, we have seen what is small a. Small a is equal to small x plus small y plus small z. So obviously z will be equal to a minus x minus y. And let us know this is equation number 30. So in this way, now we have expressions for the concentrations of A, B and C. In other words, the expressions for small x, small y and small z. Okay, so substituting the values of x and y in this expression, because we have derived an expression for x, we have derived an expression for y. So substituting those expressions in expression number 30, or in other words, substituting equation number 7 and equation number 12 in equation number 13, we get, let us see what we get. So let us substitute equation number 7 and equation number 12 in equation number 13. So z is equal to A as it is minus A into e to the power minus k1 into t. We have seen, according to equation number 7, x is equal to a into e to the power minus k1. What it is? X. Okay. X minus y, k1a upon k2 minus k1 into e to the power minus k1 into t minus e to the power minus k2 into t. Okay. This is what z is equal to this. Okay. So z is equal to this, and let us suppose this is equation number 14. Now we can write this equation number 14, taking a common, and the e to the power to the power minus k1 into t minus e to the power minus k2 into t, and rewrite this equation number 14 in little bit different way. Z is equal to a upon k2 minus k1 in square bracket, simple bracket, k2 minus k2 into e to the power k1 into t minus, in another bracket, k1 minus k1 into e to the power k2 into t, small simple bracket closed, square bracket closed, equation number 15. So in this way we have seen expressions for x, y and z. Okay. So when we plot what the concentrations of reactant A, reactant B. Why I am saying reactant B? Because reactant B is no doubt the product generated in first step, but for second step reactant, the product B acts as a reactant. So when we plot a graph between the concentrations of A, B and C as a function of time t, we get the curves, and the nature of the curve is something like this. When we plot these concentrations of what? The concentrations of A, B and C, we get three curves, and the three curves in this particular case are curve for A, curve for B, curve for B, and curve for C. C. This is curve for B. Here it is concentration and time. So when we plot a graph between concentrations of A, reactant A, B and the product C, we got such type of curves. The nature of the curves is like this. When we look at the curve for A, we will see that the concentration of A falls continuously. A, concentration of A, reactant A, continuously decreases. When we look at the curve for B, we will see that the concentration of B increases up to certain extent, reaches a maximum and again decreases. Okay, so in this way we have seen the concentration of B increases initially, reaches a maximum and again falls continuously. When we look at the curve for C, we will see that the concentration of C increases continuously. So, in this way, we have seen the kinetics of consecutive reaction, a simple hypothetical consecutive reaction in which A is converted into B and B is converted into C, and the rate constants for the these two consecutive status are K1 and K2, and K1 is not equal to K2. With this, I am sure you must have understood what are consecutive reactions and how can we discuss the kinetics of consecutive reactions. So with this, I am sure You have understood what are consecutive reactions. The examples of consecutive reactions we have seen. Thermal decomposition of acetone is a consecutive reaction. Thermal decomposition of acetone occurs in two consecutive steps, two successive steps. We have seen with the help of those two reactions taking place in two different steps. We have also seen one more example, and that example is hydrolysis of diethyl succinate. In that case also we have seen how diethyl succinate gives succinic acid and ethanol, the final products, but the final products, whatever final products which we get in that case, does not the conversion of diethyl succinate does not occurs directly into the final product, but the conversion of diethyl succinate at first takes place, and we get monoethyl succinate at first, and later on that monoethyl succinate is converted into what, the succinic acid and ethanol. And at last we have seen the kinetics of consecutive reaction with the help of hypothetical reaction, A giving B in first step and B is giving C, the final product C in second step. So with this I stop here. Thank you very much for